Good evening, all. I'm Libu Manjakkal, working in University of Glasgow, Blendable Electronics and Sensing Technologies Group with Professor Ravinder Dahiya. My major work is concentrated on electrochemical devices like sensors, supercapacitors, and everything. So today, I would like to discuss with you a small portion of my work related to reference electrodes. So, you all are familiar about this reference electrochemical sensors, and in which we are all talking about sensitive electrode, working electrode, counter electrode, and reference electrode. So, before that, I would like to thank my colleagues, Carlos and Professor Ravinder, for supporting this work. Today, my presentation is basically the motivation and how I fabricate the device, and research and discussion and conclusion. So, why reference electrode? In electrochemical sensors, we are all mainly working in sensitive electrodes, in SFET and sensitive field effect transistors, or miniaturization of the device. So we can fabricate sensitive layers in a nanotube, nanostructure, in a nanoscale method. But the major problem of in electrochemical sensors or in electrochemical studies, it requires reference electrode. So commercially available major reference electrodes are glass-based electrodes. The problem of glass-based electrode is that it contains a KCl solution. With time it will dissolve and it will leak out. We want to fill again, and in high temperature it will break, and it is not possible to miniaturize. For example, in reference electrode, we need this in electrochemical sensors, you can see here, and in biosensors, and also for study the electrochemical reaction of supercapacitors or batteries or dye-sensitized solar cell. For any work related to electrochemistry, we need one of the major stable reference electrode. For example, in voltammetry, amperometry, and potentiometry, and impedance spectroscopic analysis. And these are the major pointing towards next type of reference electrode, like miniaturization, high pressure, high temperature, ease of fabrication, and low cost, and also online monitoring. And when we talk about the next future electronics or the current electronics, wearable devices, in flexible electronics, we are very easy to flexible the sensitive layer, but when we are coming to a glass reference electrode, it is very difficult. So we fabricated a thick film reference electrode. Presently it is not flexible, but we are now also developed recently a flexible reference electrode also. This is basically fabricated based on a screen printing technology. As you can see here, initially I just first discuss how I fabricate the device. You can see here an Llavina substrate and screen printed a thick film silver electrode. A silver chloride reference electrode contain a silver layer coated with a silver chloride layer and dipped in a KCl solution. So initially I deposited a silver electrode by screen printing. After that silver I convert to silver chloride by chloridizing with some chloride solutions. And then this is another major task in my work, because normal reference electrode contain a KCl solution. It's in a liquid form. So we need, in a thick film technology, we need a thick layer or a layer of KCl. The problem of KCl is that KCl is like a salt, or when we make a powder or when we printed this, it will easily dissolve in water. So initially what I did is that I took this KCl salt and by solid state reaction method, by ball milling method, make it powder. And this powder I mixed with a glass composition by ball milling method again and make a paste. And then after that I print this. Initially I did pure KCl and it easily dissolved in water, so my reference electrode have no long lifetime. The advantage of this paste is that it have a long lifetime, because here you can see that after that I deposited a insulative layer here. So a small portion is coming out to the insulative layer. This is called hydration pot. So when water or any solution reacting with this area, what happens is that the ions are moving to here, and so we can connect with our sensitive layer, and easily this potential is connecting. So this have long lifetime also, how that this part slowly decaying, but we have a large portion inside the sensitive layer, insulative layer also, and so it can long life also. Here you can see some comparison of how a glass reference electrode and how a thick film reference electrode. This is the commercial glass reference electrode, and this is the fabricated reference electrode. And here is the cross section. You can see here an hydration port, a substrate, an insulative layer, and a AgCl layer. After that, the basic study for any reference electrode, fabricated reference electrode, is that the stable potential, because we need a stable potential against a sensitive layer. So initially I did a measurement against a glass reference electrode. Here you can see an hydration. Initially, after fabricated, initially it takes some time to get the stabilization because of the reaction of the water, and initial some drift is also there. And it may be when we are using a continuous or online monitoring application, it is not a big problem, but when we are keeping the reference electrode long time in our shelf, it almost fixed, but when we dip again in the water, it get that path. So for a continuous online monitoring application, it is very useful, and I did this 2 years also. You can see here for 2 years it is working now, still it's working. And here another test I did is that this thickness of this KCl salt matrix in a different layer of thickness, and check how it's the performance against this. And I found that the lower thickness have easily stable, but the higher thickness have a long lifetime also. After that, the basic study of cyclic voltammetric analysis. Here you can see an applied potential against the measured cyclic voltammetric, and with a different scan rate, and it seems that with a high scan rate also the reference electrode is perfectly working, and the anodic and cathodic peak current shows that it is a diffusion controlled reaction. And for an application of this reference electrode, I developed a thick film pH sensor based on a sensitive layer is there. It's ruthenium oxide sensitive layer, and the potentiometric performance of this pH sensor is measured, and we observed a sensitivity of 55 millivolt per pH in the range of 5 to 8, and I also characterized this in the range of pH 2 to 12. I also did this work. I didn't show here this work in a different solutions, different interference of ions, selectivity issues, all we characterized for this pH sensor. And another characterization I did is that here you can see with the different NaCl concentration solution how the performance of this device with the stable potential. You can observe here a stable potential of this, and this thick film, against this thick film reference electrode, we can again miniaturize it. This is now almost the active area is almost 1.5 centimeter square, and we recently did a 0.5 centimeter square also. Conclusion. The reference electrode shows that 10 micrometer thickness layer shows a very good stable potential against the reference electrode, glass reference electrode, and the sensitivity shows a 55 millivolt per pH for a pH sensor. As a next step, now we are fabricating a flexible reference electrode based on PET substrate, and in that case, in here I used the cellulose as a binder for this one, and another next one in flexible one I used as a binder for a room temperature curable binder paste. And I'm thanking my colleagues. And here is Professor Dahiya, and my colleagues are somewhere here sitting here. And funding agencies EPSRC, European Union Council, European Union for Marie Curie program. And thank you.